Hello, good afternoon. Hope you're having a good Sunday. It is a very pleasant day today. It was sunny this morning, but then we got some clouds rolling in, got some rainstorms, um, and yeah, so it's very pleasant, very cool. We're gonna do some more databases today. I've been thinking about what we did last time, and we kind of finished up the Rust version of Berkeley DB, at least so far as the blog posts go. Um, there are a lot more details. I mentioned my former colleague who worked on Berkeley DB, um, and he's been chatting me up on private messaging about the series. I really appreciate that feedback from him. Um, but the there's a lot of knowledge that he has that I don't, and we don't have a whole lot of information beyond what's given in those blog posts about the contents of Berkeley DB. I suppose we could go and read, an implementation, their potential, um, copyright and and patent issues there that I don't want to get into. But what I would rather do is, having had that experience, and we started on an Elixir implementation, which is great. But I don't actually think we were going to learn that much there. Um, Maybe we would be able to get to the point of having some interesting stuff around like process management because Elixir is going to force us in that direction. But I actually want to do something slightly different, and because I think that like there's some stuff to be learned about Berkeley DB with respect to B trees, and thank you, a shout out to our regular viewer Isaac, who sent me a message. I think it was on Mastodon or something later. But the order one thing he brought up, in our like DB load put things out of order. Well, the keys in the file don't necessarily come in order, but part of the reason the offsets are separate is that you could move the offset pointers around, and that would be the sorting. So like you could sort without moving the data. Um, Interesting point. Anyway, I think we've learned quite a bit about that, about B trees, and but there are other kinds of database storage engines, and I had mentioned this I think in a previous stream, that we were going to consider looking at a tiered storage engine based on LSM trees, so log structured merge trees. Um, Berkeley DB is a traditional B tree. It is not an LSM tree. There are a lot of trade-offs that are interesting there. LSM trees are really designed for high activity, especially on writes, so that um, you can have really unencumbered writes, and you can amortize the cost of eliminating rewrites or deletes from your storage engine over a longer period of time. So consider that if let's say you had written something with the Berkeley DB format that we were looking at in the previous series, the previous several episodes, um, and you wanted to replace the value of one key. What is likely going to happen? There's lots of potential other things, but let's say that the the key that you're trying to replace, you're not replacing it with something that's of a different size. Like the key that you're replacing, or the value you're replacing, is the same size as the previous version of the value. You still have to write a whole page. you likely have to write the entire file of all pages, even if you're not rewriting one page, right? That's what that LSN number is for. Like, it decrements, you get a new log sequence number of, here I wrote this key. And that's just for a rewrite. Think about if you had to insert a value, and based on the boundaries of the existing pages, that value would cause the page that it should be written into based on the key ranges to overflow that page. Now you have to potentially rewrite multiple pages. Another option is, what if you want to insert a value that is bigger than a page? That's my buddy explained to me, that's what those overflow entries are. They're saying that this thing is bigger than a page, and here's one of the start page that it's in. There's some more details in there that I'm not going into, and I don't really understand, but that's okay. So considering all these things, the fixed size pages, the potential for needing to rearrange keys in multiple pages, the potential for having something bigger than that page size, and then consider that you're doing this rapidly. You're rewriting those things rapidly. You have the potential for churn on this kind of database structure, and that churn is expensive. So what LSM trees do is their idea is that you write, and this is common in things like Cassandra, Riak had it. Lots of other these new databases use this kind of internal structure for their RocksDB, LevelDB do this thing. But it's basically, you have the most recent keys in memory, and when you write those out to disk, that is at the youngest generation. So you could think of it almost like a generational garbage collector in a way, and that the newest values are in the lowest level of this tree, so to speak. And then as values remain unchanged, and as you write more files in this youngest generation, those files get picked up as a separate process, usually a background thread or something. They get picked up and condensed, and they graduate to an older level. So this is the essence of an LSM tree. Why is it log structured? Essentially, that means that that means that log, you think of like a write ahead log in a traditional database. The latest things are in the newest file. And merge tree, it's still a tree. You still have potentially in those files you have inner nodes which are not which don't contain the data. They can contain pointers to ranges of data, so like blocks or pages. Ooh, that was big thunder. Similar to what we have in Berkeley DB. But you're not trying to contain the whole database in one file. So where was I going with that? There are caveats to that. I don't know if LevelDB, RocksDB has changed the way it worked, but it was actually flat. And rather than having like inner nodes in the tree, it would have a skip list that you could read at the head of the file. And this would let you get you offsets into the file that you could jump to start like a binary search or a scan. Okay, so I would like to look at LSM trees, and the one that my buddy had worked on while we were both at Basho is very interesting. So let's start taking a look at that. And there are going to be some challenges here. I've already started a little bit because I wanted to get into a spot where we could go, this is our reference implementation. Similar to what we did with BerkeleyDB. This is a reference implementation. We can write a file in its format and then start to read it back in a different environment. We don't have that with this yet because it is not working on recent versions of Erlang. So let's have a look. So this is HanoiDB. I mentioned it before in a previous stream. This is by Kristen Krebs-Thorup, a wonderful guy, lots of fun, really smart. He has this whole thing with a mad scientist, wears a lab coat to talk. It's hilarious. Anyway, let's look at the design docs for this. So there's a bunch of files in here. I have it cloned. This is sort of an overview of like the interactions of each of the operations that you would do. There's a get, and this is leveled. So rather than being, an all-encompassing B tree, you start in the youngest generation. Here they're saying 8. It was actually adjusted to 10, and we'll talk about this. So we say data files at level n contain at most 2 to the n key value pairs. So in level 8, that would be 256. I think they later adjusted it to be level 10 to be the lowest level. So you'd get 1024 in each level. But that's individual files in there have at most that many pairs. And if there's misses on all those files in that level, it proceeds to the next level and scans or searches for those. So that's a single key fetch. And note, they're talking here about processes. This is HanoiDB is the gen server. It contains the nursery, which I mentioned before. That's the stuff that hasn't been written to disk yet. And then it has plain FSMs. I'm not certain why there's this. We might need to do some maintenance work on this to get it to actually work. And there's one thing that I was trying earlier that actually broke. And it's because the Erlang community has moved on from Rebar 2 to Rebar 3, but there's some components of this that were from the Rebar 2 era and don't work. They don't compile. You can't even compile the tools that's used to compile them. So we're going to have to potentially remove those things or find workarounds. Anyway, that's what a get looks like. For a put, so it adds to an in-memory. So they use a GB tree. Like if we were going to redo this in Rust, which we'll probably try if we get there, this will be a hash map or potentially a B tree map. So this is general balance trees. That's what GB tree stands for. We'd probably use a B tree map, and then our stuff would come out sorted. And then, when the nursery's full, it's written to nursery.data. So the big thing here is that nursery.log so this is you mentioned a log structured. So when you go to recover, you could read this nursery log file, probably be a binary log, and get the keys and values that were inserted. And then when it's full, the data is written to nursery.data, which is a B tree. Then that file is closed and passed to the top level, and that level decides is it A, B, or C. So it keeps at most 3 files of that level. And then an incremental merge is issued, which will flow down the levels instruction. Merge processes do 200. So this is not 256 steps. Is like I don't know where. We'll have to look at the code. Hi, Maciek. Good to see you. Thanks for coming. Okay, so we'll have to figure out what steps is. I think it has to do with rewriting files or merging files. The idea, though, is when you merge these files together, it writes out this, X file, and that file might get promoted to the next level. Right, so A and B files are deleted, C is renamed to A. So it's like fill up A, fill up B. When you get to C, start merging A and B into into X, and then files get renamed and put into the next level. So at 8, this would become like A, B, or C9 after it's complete. So in contrast to something like LevelDB, RocksDB, this this merge can happen on any write. So any write that overflows the current level could trigger a merge. And in this way, this is different in that you don't have a bunch of background merges in the same sense. You actually do a tiny bit of merging, or potential for a tiny bit of merging, on every single write. This does have a cost in terms of throughput. Like LevelDB and RocksDB have insanely good throughput. Cannot deny it. On the flip side, you will have fewer pauses. The cost is amortized across more writes than it is on something like LevelDB and RocksDB. Okay. So yeah, they're saying here the 256 steps guarantees that when an inject happens, so like a new key, the target level does not have a C file. That is, there is room. So, you know, A and B get merged and removed. This gets renamed to A, and then there will no longer be a C. So we don't overflow that level. Snapshots are super interesting. So if you wanted to scan files, fold over all of the contents of the database, you can hard link, because what this merge is doing, yeah, you're writing this new X file, but you're doing renames. So if these files are currently being merged and you want to scan them at the same time, you can hard link them into new directories, which is what this does, and then that data remains until this scan process is done, at which point it unlinks those, and the original files are either, you know, deleted by unlinked by the original level if they've been merged, or they're left alone. So you can get like pretty cheap snapshots with hard links. Okay. Let's see. And, you know, there's stuff here about back pressure with, you know, how many messages, etc. And then there's a blocking fold, which I think prevents writes. I think that's what that's saying. Okay, so they're saying this is only using Riak's list buckets. Yeah, I don't know that we would need to support a blocking fold. I think the snapshot fold is really clever. And then there's stuff here about the file format. You know, it has a magic 4 bytes at the front, says HAN1. I think in the code it's actually HAN2 now. But we can kind of compare and contrast this to the B-tree Berkeley DB that we've been doing. You know, it's a series of blocks. The blocks have and there's a trailer. The blocks have a particular format. There's a length, level. So this is like similar to Berkeley DB. Level 0 is a leaf node, and it counts up. So if you need more inner nodes to capture the contents of this, then this gives you, you know, that log base 2 of n for both gets and puts and so forth, and scans. Okay, so then, you know, this is saying you have this block len includes the level, so you have 2 bytes here for the level, I believe, and 4 bytes for the length, and then, you know, the rest of this block is including those 2 bytes. So you have block len minus 2 for this. Interestingly, at the end of the file, there's a bloom filter. This is currently using eBloom. I think eBloom might not be working. We'll find out. So the bloom filter is a quick check of, is this key even in this file? It can give false positives, but it never gives false negatives. So if the key is definitely not in the file, it will say no. But if it might be in the file, you're not sure. It could say yes, even if it's not in the file. Bloom filters are probabilistic, membership sets. Okay, and then so this is kind of similar to what we saw in the Berkeley DB, going backwards from the end. This trailer has the root position points to a block of the root of the tree, and then there's how long is this bloom filter, and then the bloom at the end. So you could potentially jump to the end of the file, read back 8 bytes, read back 4 bytes, read the bloom filter, and then you have you can check, you can deserialize that bloom filter and check whether the thing is in the file. This might be kind of interesting to decode. I'm not sure whether it's in Erlang term to binary format. It might be custom binary format. I'm not sure. eBloom, I think, was C code. So there's potential here that this is actually in C code, and we can figure out what the format is. Okay, so inside each of the blocks, this tree node data, there's a 1 byte flag of is it compressed. Snappy is actually the thing I'm having trouble with. So we might need to turn that off if we're going to get this to run on a recent OTP. And then there's an 255 byte, just kind of interesting. It's a little like marker. And then there's key value pairs, sequences of key value pairs. Okay. And then each of these key value pairs has a length, a CRC, so checksum, each of those 4 bytes. And then there's various flags. Is this a key and value entry? Is it a deleted entry, which contains only the key? Or is this an inner node? So they say position and length. So what block, what's the block position, block length? I don't know. We'll have to look into what these actually do. And then the key bytes. So what is the key? I'm assuming this is like, here's the beginning of this block. I don't know what the block len is in there for, because that's at the beginning of the block. Interesting. Okay, but note that this is also 8 bytes, which is the same as root position. So I wonder if what this is this an actual absolute offset into the file? And then this is so you could potentially read the entire block without having to look at that beginning of that block. Okay. And then here's this marker again. So there's a marker at the beginning of every entry, and there's a marker at the end. This note here, this is about recovery and repair. So if the file is potentially corrupted, it could find the boundaries of keys where they are FF. So it always starts with FF. It ends with FF each entry, and so you can find those signal bytes potentially, and resync some things that might have been incomplete writes. And then you can truncate. Like if you run and there's not an ending, 255 byte, you know that entry is corrupted. So that's kind of interesting. Again, this is subject to the CRC32 check. So there's there's levels of integrity redundancy in this. In addition to these other accounting things at the top, you have each entry having a checksum, which is good. Okay, so that's an overview of HanoiDB, how it's structured, what the data format is. Let's see if we can get it working. So like I mentioned, I tried to get it started, and it didn't have a good time. The community's moved on. We have some things to to fix here. Interestingly, I think everything except Snappy worked. Yeah, so like it got to Snappy. It's trying to run this enc, which I suspect is compiled for a different version of Erlang. It's like a compiled E script. And so it's like, hey, I don't have that op anymore. Yeah, that's not good. So I think what I'd like to do, I looked into, you may have seen just a second ago, I was in here. I tried, hey, let's build this tool. And it's like, hey, I don't have this. Yeah, because this is a rebar 2 thing. I don't understand how this was expected to work before. So that was a dead end. I thought, oh well, I can compile this particular tool with a newer version of Erlang, and then copy it over and get the thing. Um, I don't. We might try um, forking the Snappy, and updating it to compile with rebar 3. I think there's nothing specific about, other than maybe stuff like this. I'm not sure if this is going to work. Look at how old those versions are. Fun. This is like they were when they were making huge changes to the NIF API back in release, because it was like new in release 12 or 13. It was unstable in release 14 of OTP. And then it got more stable after that. We're long past that those era. So I wonder if there's any way we can make this compile without this enc tool. No, we do have, I think, some of these have port specs. And oh yeah, so is it SEXT? Unfortunately named. No, I think it's LZ4. No, that's port ENV. There's one of these, maybe it's eBloom that uses, yeah, so the folks who work on React day to day have updated it to use the port compiler plugin for rebar 3. Andrew Thompson, 6 years ago. Hi, Andrew. And I wonder if we can just trick it to do that. Let's see if we can do that before we go through this goop. Let's say plugins, like they do PC. Hi, Chris. Good to see you. Thanks for coming. Yeah, let's try that, and let's, instead of these, let's copy the hooks that are in this one. Provider hooks okay. So we'll do that, and let's see if we can build that without this enc tool, which is the Erlang native compiler thing. Okay, we're gonna have other problems. Okay, logger. Yikes, logger's so old. OTP has a logger. Okay. Trick is random uniform use. Okay, so that's going to be easy to fix, I think. Let's look at this one. That's interesting. Okay, what I'd like to do, rather than try to fix logger, I think we can fix trick real quick. I don't recommend doing it this way. We'll probably need to make a fork and apply these things. Let's find tricks datem. Yes, please install the Erlang. Thank you. Okay, line 115. Let's use rand. And 119. Let's use rand. Okay, and for logger, I think I'd like to replace it with the Erlang logger, in which we should do is that part of standard lib. Let's find out. All right, logger. So that's part of kernel. Okay, so we don't have to explicitly start it. What we can do is potentially replace all the places that we use LAGER, as in the beer, with LOGGER. So maybe let's have a look at that. Okay. In the meantime, let's see if we can compile trick. Didn't I just change that? I did. Did I save it? Random. Use rand module instead. What? Oh, statem FSM. Okay, so it's in a different file. Sorry. Random rand. That looks suspiciously similar. Oh, it's Tuncer. Wow, I haven't heard that name in a long time. Got Tunst. Okay, this one has Erlang get stack traces removed. Random seed, use rand module. Okay, so the thing that's kind of annoying about this is I think it's following file dependencies, and it's not compiling everything. It gets spoiled by Rust, honestly. 171. Okay, so this would be, we'll do stack trace. And then 469, another random thing. Generate randomness, rand seed. Okay. Okay. So I think we're going to need to do a lot in there. This is trick DOM. And we're going to have to refine and replace random with rand. And let's put a colon there. Yep. All those places. You know, it's funny. I had a discussion a while back with a friend about OTP and like how many things they don't change over the years. Like super stable. I think it's partly, you know, strategic on the part of Ericsson, that they have products that have been around for decades that they need to support. And so they try to change things very carefully and very slowly, especially as far as like what's available in the standard library. And this is one that I'm like, wow, you could have done a little bit better on that. Okay, so now we're into errors with Hanoi. This is progress. We need to look at plain FSM potentially. We might see if we can replace that with statem. I'm not sure what the differences are, because plain FSM is, you know, a library somebody made. They didn't like gen FSM in OTP. Yeah, so sys get debug, they mean sys, that's been replaced with sys get log. So we'll have to look into that. Okay, and we've got some pretty standard things here. In the past, I've used rebar scripts to fix this particular thing. Yeah, the languages and interface doesn't change much, but implementation underneath does more often. Yes, absolutely. Like the Bean, they're adding new opcodes. They've got JIT. They've got all sorts of crazy stuff that's new. But yeah, they very, very rarely change the standard library. This is a case where they made some pretty big changes. Okay, so honestly, let's just see if we can fix this. What I'd like to get to today, if we can fix all these compilation errors, is the point at which we could run a script that fills a Hanoi database with some information, and then look at it. Yeah, that would be good. Okay, fold worker, line 84. The Yeah, let's do that again. Stack trace. Oh, and we'll replace that. Okay, merger. Line 60. We got a similar problem. I don't know why this is so inconsistent. But there we go. Yeah, at one point, I think during this transition when they were going from, you had to call the BIF get stack trace like this code is doing, and when they actually put it as part of the match pattern on catch, I think I wrote some pound like some header files that would define that based on what level or what version of Erlang you were on. But now it's such old like ancient history at this point. Like, might as well just change the code directly. Okay, so we got merger line 6061, util line 302. And my apologies, this is not the most interesting coding, but we're going to get exit error stack trace. Oops. Colon. Wow, that's great. That's great. Okay, util, let's look at Bloom. 234. That's not right. Oh, functioning bit array news unused. Okay, I'm not gonna. I'm not gonna deal with that, I don't think. Let's look for bit array new in the entire there. Okay, so I should get it to ignore build. Yeah, so this is not called from anywhere. That's actually a valid thing. Let's just comment it out for now. Okay, HanoiDB hurl. No, Earl, not hurl. 215, another stack trace thing. Okay. And let's save that. And reader. We're getting toward the end here, folks. 380. One thing I especially want to show you, because I think it's just fun, and it's where this storage engine got its name, is we can, while we're running a like a benchmark to fill the thing, fill the database with data, we can do a visualizer. So it's got this, so it's got a BashBench driver, which is fun. We may need to like get BashBench to work on a recent one. Um, and then this script, uh, which will, every second um, print out information about every level in the database. And then and you'll see like it looks like an algorithm doing Towers of Hanoi. So that's how it got its name. Um, so okay, HanoiDB level 53. What is this? Record state has fields without type information. Okay, we're not gonna bother with that. Don't care right now. I don't know what these are, and I don't care. That's just a warning. Okay, level 164 is another stack trace thing. $12 years ago. Okay, I think that's all the warnings. Let's have another look and see. Okay, so we have one I missed on line 85 of fold worker. Yep, just flat out missed it. Okay, so we're missing a description entry. Big deal. Description. I don't know. LSM tree tiered storage engine with amortized merging. Okay, fine. Now rebar 3 is happy. Okay, so let's see about. I want to look at the make file and see if there's like a bench target in here. There is not. Yes, fine. Make files. There is not a bench target. Let's see if we can run the tests. Yeah. It doesn't have proper. I think that was probably they were trying to use trick instead of proper. But the tests refer. Okay, so we need to define if def trick. Okay. Let's see. Maybe we can update the rebar config to do the right thing. By the way, I had to update these so they actually point to Git repositories that exist. That was fun. Oh yeah, so here's BashBench. Let's see what's going on with that. BashBench. We're getting old history here. 7 years ago. Okay, so at least it's more recent than this code. The primary branch is master. R16. Woo! Fun times. So it is, the branch is still master. Let's add it. See if we build BashBench. This syntax is probably wrong. Yikes. I've had this actually time out. Yeah, it can't fetch that because it doesn't have .git on the end. I changed all these to HTTPS. Let's see if there's BashBench in here. We'll fix its rebar config. Yeah, let's replace Git with HTTPS. Okay. And oh my goodness. And then these need to have .git on the end. Excuse me. I have no idea whether, hey, there's one. JJ, get opt from JJ. Cool. I have no idea whether these other dependencies are going to work at all. Juan Jose Comelas, who Maciek and I worked with. Oh, did I save that? No. Save. Let's try it again. The yeah. The other thing that is interesting about this is that, you know, I mentioned before the Riak community has continued even after Basho was gone. Little history there. You know, Basho went down in flames. It was really depressing to watch. But some of the users of Riak wanted it to continue so that they could keep their installations up and so forth and continue adding things to it. So a company called Bet365, once Basho was in receivership, they purchased the intellectual property of Basho, and then they explicitly opened up everything to the community, including the things that were previously enterprise features, you know, like multi-data center replication and whatnot. So because it was in their interest, they were using Riak. It was in their interest, in the interest of other people in the community. Yeah, this is like transitive dependencies. It was in the interest of other people in the community to have that stuff available and open so that they continue to operate and, you know, do maintenance. Anyway, so there's like, when I left Basho, I think we were version like 2.2 or something of Riak. There's now like 3.4, 3.5, 3.6 going on. So it has moved on. They've, you know, kept up with a lot of things, not been evenly distributed necessarily. But what I was pleased to find is that one of these dependencies was actually up to date and compiled just fine with rebar 3. So that was good. Okay, so we can't get that dependency anymore. I wonder if there's a Basho fork of it. And I think this is from, let's look for bear.git. Okay, so that is in Folsom. I wonder if Basho has a fork of this. Joe Williams, 12 years ago. Joe Williams. Okay. Let's see if we have a fork of bear. There is. Okay, so there's a fork there that we can use. Let's do that. See if it's referred to from anywhere else. Rebar locked. Wow. Okay, so that's in test. Don't need to worry about that. All right. This is the sort of thing that happens when you try to get a really old piece of code to run again. Yes, yes, Maciek. We need to ask what I'm ask Mahesh what JJ is up to nowadays. I have not heard from JJ. I don't think he was ever that big on social media, but you know, with the decline of Twitter, I will never call it its new name. Yeah, I don't hear from him. Hi, Isaac. Yes, we're resurrecting HanoiDB. Thanks for coming, and also thank you for your comments on after the stream from last time. Okay, yeah, that's not going to fetch. We're going to switch that to HTTPS and that one to HTTPS. The other thing is we need to make sure that there's tags. Okay, so the tag we're trying to fetch is there. Yeah. Yeah, it's fine. Yeah, it for whatever reason, Rebar 3 does not like those sorts of Git protocol URLs. Yeah. Let's call it Y. Like why? I agree with you, Machek. Honestly, God, I wish Twitter. I wish I could quit you. I have been enjoying other social networks more and more lately. Much less enjoying Twitter. Okay. Maybe what we could do rather than trying to get BashBench to work. Let's remove that. Maybe what we could do is write something along the lines of, or that uses this script. And we could just start filling a Hanoi database with a bunch of stuff. Because what we care about here is not necessarily what is the performance of this code exactly, but you know, what does a file look like, or what does a set of files look like? Because it's actually a directory. Okay, so just to talk, let's talk briefly about what this file is. This is a driver, so to speak. So BashBench is a generic benchmarking framework, but specifically for working against databases. There were times in my tenure at Basho that I would use BashBench on site with customers to test whether their setup was going to work. There was actually one customer who shall remain unnamed that I worked with on site, and I ran a benchmark. This seemed like it was going great, and I was like, this is going to run for 6 hours. We want to like really bake this in. I came back the next morning, and the throughput had tanked. It was like 0.1 writes per second. And at the time they were on they were on AWS. And this is before, like, nowadays, like, everybody's on AWS. And at the time, like, you know, virtualization had a much bigger cost than it seems to nowadays. People run, you know, databases just fine on cloud nowadays. But at the time that we were doing this, we were kind of discouraging people from using AWS because the performance just tanked. But in this case, it was actually that I don't know if they were writing to local storage. I don't remember if that was local storage or if they were writing to EBS or something like that. But their cluster was 5 nodes, and I think it had 1,024 partitions. So that meant each, or maybe it was even 256, but it was still way too many. Each node had hundreds and hundreds of processes all trying to write to disk at the same time. And since they're all writing to the same disk, you weren't getting any, or like the concurrency on writes was too high. You weren't getting good throughput because they were all sitting there waiting on the disk. And so what we counseled them to do was to decrease the partition number such that there was less concurrency to disk on each node, Now, I think that they were thinking, oh, we need to get this to be a really big cluster size. Actually, I think the largest cluster size I saw was in the 30 nodes or so. And that was big. I'm sure people have done bigger ones since. But like you don't need that level. And what is actually happening is there was so much contention on the disk that the throughput dropped off after like an hour. You remember I set that benchmark to go, and then I left to go back to my hotel. And then I came back in the morning and it had run 6 hours, and it was like, you can see the graph, it was like, it was really depressing. Anyway, okay, back on topic. We had ones that would use the Riak client. We had ones that would use our storage engines directly, so you could benchmark the storage engines. And so you would basically define this driver. It would have its own internal state, which was managed by BashBench. And it would be like, new would set anything up that you needed to set up, like create a React client or start the level DB backend or whatever. So you'd get all this stuff out of the benchmark configuration. And then you'd start up any processes that needed to be started. And then your benchmark config would give you a list of, here's like the operations that I want to do and the mix of them. So like in that benchmark that I mentioned, I did mostly writes, but I think I did like 25% reads or something like that. And they'd be like get or put, and you can use these generators that are injected by BashBench to decide what keys and values should be written or looked up. And these were you could specify the distribution on these keys and value generators. Like the value generator, you could say how big should the value be within a range. Like, are you using uniform or using a bell curve distribution, or are you using like sort of like a Poisson distribution or something like that. This is very useful for building up like credible benchmarks. Anyway, so get, put, delete, and then there's fold. This is like fold over 100 keys, it looks like. And okay, so what I would like to do is maybe just make a script that similar to our what we did for Berkeley DB. Let's open a Hanoi database and put a bunch of data in it, and then we can start poking at it. That could be good. So let's see here. We kind of want an E script, I think. Alternately, what we could do is make a source module. Yeah, let's do that. HanoiDB load. Okay. Let's just make something that's like run. And this will be a directory. Wow, I haven't written Erlang so long. Okay. What we want to do is let's split right here and we'll look at this. We want to do something similar to this. And what we'll do is we'll compile this and then we'll start a REPL and just run it. Okay, so they're like directory file name test.hanoidb. config, we'll just use the empty config. So let's do case HanoiDB open. Are they, so they're joining file name. Yeah, let's do file name join dir. We'll do something similar, HanoiDB. And no options. Error, reason. We'll just return error reason. Yep, it is semicolon. I haven't forgotten that. Okay, so this is OK tree. And then we probably want to make a new function that's called fillDB and just pass that. Okay, fillDB. And let's do something like this. Let's put, I don't know, 100 entries in there. And actually, if we get this, we want to do, there's probably like a close. There's close. Yeah. Oh, language server's not working. Right. Okay. So yeah, we'll call close at the end. HanoiDB close tree. Okay, so what we're going to do, this is tail recursion in action. We're going to do some stuff, %, and then we'll call fillDB tree and -1. So that's just classic tail recursive. Okay, so let's do the interesting thing about BashBench is it has generators for keys and values. Like, I think we can probably use crypto ran bytes for the values. I don't actually care what the values are. Or we could do something similar to what we did in BerkeleyDB, which is write keys and values that just have letters. Maybe let's try that. Okay, so let's say letter is n mod 26. Okay, and then let's say length is rand uniform. Let's look at the docs for that. Rand uniform. Yeah. I'm talking. What? Rand uniform. Let's say the value length should be rand uniform, like maybe most 100 characters. This is not, like, we don't actually care. Let's just say length. Yeah. Okay, so then we're going to need key. And let's do a binary comprehension here. We'll do a similar thing for value. And we're going to say Percent is not right. It's mod 26 plus A. So this is character A. Does that look right? No, or is it that? It's that. The question mark is Elixir, not Erlang. Okay, so then we're gonna say UTF-8. Is this how you do this? I've forgotten binary comprehensions in Erlang. Let's look for binary comprehensions. Comprehensions. There we go. Okay, yeah, so we can do this. And you can do it with maps as well. Okay, so we'll do it with ignore comes from list seek 0 length. Remember, we're not going for we're not going for speed here. We're just going for fill the database with something. UTF-8. And we'll do the same with that. Honestly, though, we could just say this and HanoiDB. Let's see what the API is there. Nope, not the header file. Not the actual file. Put. Okay. I probably could have looked at the, yeah, so ref key value. Okay, so we'll say put, and those are both binaries, right? Okay, we'll say key, put tree key key. And then this will return, honestly, let's pattern match on OK. Because I don't want this to, like if this doesn't work, we should just blow up. I think that's reasonable at this point. Okay. Let's see if we can compile that, or if I'm a bonehead. I don't care about mech. But the problem is now we've got all these dependencies in here. Let's just see if we can delete mech from the build directory. By the way, I do not recommend doing it this way. Delete that. Snappy depend on that? No. Is it Bear and Gold Rush? And let's see, I think it's probably Bear. No. Let's run that with debugs is 1. Gold Rush. Does that depend on mech? The one thing that is also frustrating, no it doesn't, is there used to be no difference between build time and runtime dependencies, or rather like your runtime dependencies were defined in your app.source file, but you still had to pull in things to build it even if you weren't running tests, and mech is one of those things that was always frustrating. Okay, so I deleted it and it didn't go away. Did it fetch mech again? Honestly, we're just going to have to search for it. Mech include build exclude source test. Okay. Folsom requires it for its tests. Yeah, okay. I think, so I think we need to delete BashBench. We need to delete bear. All these things that were not part of, and the rebar config, or rebar lock. What is it? Unlock? See, it's fetching it again, even though I don't use it. Okay, so I removed it from the depths here. So I think what I need to do is remove all of these from the lock file. Yikes. Okay. Wait a minute. Let's see. Okay. Trick snack VP. GPB. That would be Katya. Okay. So another dependency of BashBench. I'm not sure where this is coming from. Maybe if I try unlock help. Okay, let's say BashBench. So it's not in there. And mech, and yeah, let's just get all these things. CasBench, CQURL. Wow, Semver UUID. Sometimes I think, like, you know, and it's true, JavaScript ecosystem has a dependencies problem, but this is a mess. Yikes. Get opt. Eyebrows. Katya. Mochi web. Node package. Wow. Before there were actually tools like Deps plugin. Riak C. Riak PB. Hamcrest. What is Hamcrest? I don't even remember that. Okay. So let's make sure that those things are removed. They were not removed. Well, Well, that's frustrating. Okay. What did we do for the depths? R3 tree. Okay, so yeah, okay. So this is showing these things aren't in here anymore. We can delete those. Um, except it didn't. Here, let's close everything. We'll come back to that. What's in here? Okay, so that's different. All right. Let's just do this like so. BashBench. CQ Earl. Folsom. Bye. Hi OBS. GPB. Hamcrest. Eyebrows. Yeah, there's all these dependencies that BashBench requires that like are completely unnecessary for us. So MochiWeb, node package. It's ridiculous that it includes that. It's so weird. QuickRand. Excuse me, LockDepths plugin, which is hilarious because that's a thing in Rebar 3. Riak PB is not needed. Riak C is not needed. Semver is not needed. And UUID is not needed. Okay. Let's see if we can compile now. Okay, so I have a problem in syntax. That's what I wanted to get to, for Pete's sake. Okay. Line 16. What did I do wrong? Rem 26, not mod. Okay, so I think what this means is we do this. Let's see. Fill DB. Okay, this needs semicolon. Again, refreshing my knowledge of Erlang syntax. Okay, so let's do Rebar 3 REPL. No, what is it? Shell. Okay, application, ensure all started, HanoiDB, right? Okay. So HanoiDB is started. Let's say let's try our script. And we're going to say, I don't know, data. Okay, so there... Let's try it with dot current directory. Okay, so that ran really fast. If we look at... now, there's only going to be one file, right? Because the base... we only did 100 keys. Yeah. Let's run it for more. Here, let's delete that directory. And then let's run it for like 5,000 keys. Now the problem is this is going to potentially, overwrite some things, but that's okay. Okay. HanoiDB load, run, and we'll say current directory. So this is going to do 5,000 keys. It's still blazing fast. Okay, but you can see here we've got an A at level 10, and then an A at a level 11, a B at a level 11, and X at level 11. So we might do something here like let's run it again, see what happens. Okay, so now we've got stuff at level 10, level 12. Level 11 is skipped, so there's nothing in level 11. It looks like they were being merged. There's a nursery.log, which is binary. No, that's not right. We don't want to actually look at that. I suppose the nursery log should be empty at this point if it's written all to files. Okay. Well, I think we have some stuff we can look at. So what I'd like to do now is see about doing this in a separate language. And we've been going for about 90 minutes. Maybe we can get going. I'm up for doing more than we normally would. So hopefully things are going okay. I see OBS is concerned about connecting to chat. Did anybody experience dropped frames or anything? Okay. All right, so let's make a new Rust project. And this should have this should be a bin crate as well. HanoiDB. Let's see, cargo, new, help. So path. So we'll set the name differently. Bin name is HanoiDB, and we'll make the directory HanoiDB rs. Okay. And what I'd like to do is try to go by the docs that are in this project, and we will see if we can't. Now, the eBloom is something that I might want to change. Maybe we should redo our script here real quick before we go and open up the Rust code. Because there's options here that we can probably specify for which bloom filter to use. The other thing is we can look at the source code of eBloom. It has, there's the nifs stuff. I think it's a C++. Yeah, and I mean most of it's defined in this header file, if I had to guess. I don't know why this is C++ and not plain C, but yeah. Let's look at this. Oh, okay. So this is somebody's code from 2000 for a bloom filter. This is why it's C++. Yeah. Classes. I don't know if I have the brain to parse all of this. So what we might do is when we do our implementation, ignore the bloom filter that's in the file and use a bloom filter that is in like crates.io or something. Which will suck if we're just like, oh, let's try to read that. For now, we can just treat it as opaque bytes, right? When we implement the trailer. Okay, so let's not worry about that. I wonder. So the file format should have HAN2 in it, not HAN1, like it's in the diagram. See if there's anything else that we need to know about here. Let's see if that was actually configured in rebar config. It might be using the scalable bloom filters, which is a pure Erlang implementation. It is. Okay. So it does use eBloom. Oops. I'm sorry, we were looking at the header file. Yeah. Right, and then it calls that. Okay, so here's the stuff on the on disk representation. You remember we had see you Maciek, thank you for coming. Remember we had in here, this is key value or deleted or position length. That's what these tags are. So we will need these. And these are hexadecimal, right? So we will need these when we go to implement the Rust version. I'm guessing that there was a file format change between HAN1 and HAN2. Just out of curiosity, let's do head C4. Oh wait, I'm in the wrong directory. I was about to open the new one. Okay, let's do head C4 test.HanoiDB A10.data. Yeah, so they are starting with HAN2. It's not clear to me. Yeah, then the nursery log is truncated because he closed it. It wipes the log. Okay. Interesting. Note that that's like bigger than the level 10 by a significant amount. Those merge things are only 4K. Interesting. Okay. So what I'm assuming is that it'll be using kv data 2 tag and deleted 2 rather than deleted and kv data. I'm guessing this does not change. Of course, the end tag is what we saw before in the design document, that like that each entry, is preceded by and ends with the, FF byte. Okay. All right, so we're getting to Rust. Sorry you were unable to do that with us, Maciek. We will catch it on the video, and we'll probably do it again next week. So you won't be missing too much. Okay, so let's open a new window with all this. And, our main is not going to do much. What we will probably do is we will get We'll get the directory. Directory to read. We'll start with that, and then we'll just print line dir. I just want to make sure that we get this to call skip next. Oh, we just call nth, right? We ran into this when we were trying to. That was hilarious. When we were trying to really read Berkeley DB files, it was passing it as a command line argument, and it was reading the binary, like its own file. That was pretty funny. Okay, so let's just make sure we can cargo run this, and yeah, required directory to read. Okay. And then we'll say test.HanoiDB, and it's not there, but we know that we are getting the argument through. Okay, so I think we want to get quickly to Camry read this thing. So let's make a new file, which is we'll do this stuff, right? And let's just call it format. Yeah, let's just call it format. We can rename it later. And then we will do mod format just so it's there. Okay. So we're going to need some different data structures. Let's think about, we don't have CRC32 yet. We may need to find a crate that does that, or an algorithm that we can implement easily. Yeah, so let's think about the structures that we need here. We need, we're going to need something like a database, like we did before, and we could do, we could just do this. The thing is, it's not going to be that. We're going to have more than one file. So maybe this is like, file's the wrong word. Maybe we want a tree. Maybe we'll call it a tree. And let's do, for now, vec u8. I think that we don't, in the end, we probably don't want to read everything. But we can do that for now. Let's say from file. And we're going to say as ref path buff path. That's impl as ref path. And this is going to be result self. We'll say IO result. Standard IO result. Right? And we should do is it fs read? Yeah. Say let data is read path, and then we'll say self data. Okay, so really dumb. Yep. And this should be okay. And this is pub. Okay, so now we should probably in here do some validation. Um, and something like this, except we want HAN1 as bytes. And so this needs to be an IO error, I guess, or we need to do result and use something like Boxstein error. I don't know. Let's look at, or switch into Rust. Standard IO result. IO error. No. Yeah, let's look at that one. Known kind of error. Say other. Okay, so we could do. This feels like we should be using anyhow already. Just say error other. Okay. Invalid tree format. Now this actually needs to be HAN2. Okay. And let's do. Let's look at standard FS. I think we can do something like, yeah, let's do readdir. And readdir is an iterator. And what kind of item does it yield? A dir entry. And you can get a path from that. Okay. So let's do like file is, jump back, where were we? FS readdir, dir. Yeah, asref path. Okay. And this, we'll say expect argument is not a directory. Okay. Yeah, they use question mark there. We could use result, I guess. Neat directory must have at least one file in it. Okay, so we're just being a little bit picky here for the first pass. And this should be a dir entry. We'll say path. Okay, what's wrong? Oh, readdir expect. Okay, so that's option dot io result. So that could return none. That is weird. Okay. We're just saying dunno. because we want to unwrap that as well. Maybe we'll just say unwrap here, and we'll get whatever error happened. Okay, so this should be a path buff, right? And let's do from file, expect didn't load file. Okay, let's try this. And I'm gonna do HanoiDB test. Okay. So we should have gotten all this, right? We did. Let's cargo run. Okay. Field data is never read. And we didn't get any errors. So that's good. Let's do something like print line reading file. Path buff. Or is it display? Yeah, it has a display method. Okay. Okay, so it decided that B10 was first. That's fine. I don't care. You know, the order is undefined. You should not rely on it. Okay, so we could, yeah, we can start to look at what is the contents of this thing. So okay, so we should have, you know, it did succeed, right? We didn't blow up here, right? Because we did expect didn't load file, and it didn't have a problem with that. So what we need to do is look at the trailer. I think that's the first part. So let's make, I don't know that it needs to be pub, but we'll make it pub anyway. Trailer. Okay, and that's going to be Bloom is going to be, and this is again where we're going to start to use lifetimes. Tick A of U8 slice, because we're not going to deserialize that Bloom filter yet. We just need to know it's there, so that everything else in the file, we don't expect this contents to be part of a block, right? And we'll say Bloom len is, that's going to be a U32. And we're going to say root position is a U64. Now, I'm going to, we'll have to look at the code. I'm assuming this is in Big Endian, which will be interesting. But let's look at what, I think it's in level DB, HanoiDB level. Or no, writer. It would be in writer. Yes. Okay, so accepts only monotonically increasing keys for put. So the sorting happens in the nursery. That's good to know. Okay. Let's look for things where they're constructing bit syntax. Okay. Not sure why this is using term to binary for serialize and deserialize. Interesting. Okay, so here's the trailer, right? Okay, so it's turning the bloom filter into binary. It's asserting that it's now a binary. It's getting the byte size for the bloom filter. And right, so we ran into this last time with Elixir. These are big endian. We'll have to contend with that. So this is 64 bits, unsigned, bloom, you can see, and then there's a 0 byte, which is interesting. Okay, so we have to assume that those are yep, we have to assume that those are big endian. And 0 doesn't matter. Okay, it's not a 0 byte. That's a 0 32-bit integer. All right. Okay, so let's see if we can read the trailer. So and we'll just for now assume that the compiler can fill in that lifetime. Okay, so we need to get the root position. We need end is self.data.len. And so we're going to have to do this stuff again. We're going to do self.data, and we're going to slice n minus 4 to end. Try into unwrap. And this is not from, this is from big endian bytes. Okay, and we're going to do something similar for the len. This can be U32. And we're going to have to do n minus 4 here, and this is, I'm sorry, not n minus 4, that needs to be n minus 8, right? N minus 12. And then and let's go ahead and put derive debug on this, because I'd like to print that out. Okay, so we've got the length of the bloom filter, and then we're going to do bloom is going to be self.data. This is going to be bloomlen. Except the thing is, this needs to be usize as usize. And minus 12. Does that make sense? Because we know what the length of it is. We need to read back that many bytes, and we're starting at n minus 12. I'm probably going to be off here. This is probably wrong, but we'll find out. And let's do bloomlen root pause. Now, also, if we correctly get, yeah, we need to borrow that. If we correctly get this, we don't necessarily need the length, but we'll keep it in there for now. All right, so let's do let tree. Okay, and then let's debug tree.trailer and see what we get. Okay. So we got the root position in the file is 9804. The bloom length is 1304. So that's a huge bloom filter. I need to make sure that we are doing big endian bytes. Yes, we are. Okay. The other thing that we should do here is we should check. Let's pull this out into a variable here. Whatever. Okay. Let bloom beginning start. Let's do this because what I want to do is also slice let's get the padding there that we had, because I want to assert that that is all zeros, right? We can just do this. So if we say self.data, let's slice it. Bloom start -4 to bloom start. Four bytes. We want to say not equal. Then we'll panic missing trailer padding. And I don't recommend, we're just trying to get into here. Like if I were trying to make this production code, I would not have unwraps there. This would be like results everywhere. But we can convert that into non-panicking versions later. Okay, so it still worked. Let's, yeah. Oh, I didn't save it. Haha. The problem is that's a slice. I don't know, the compiler's fine. Okay, and it still ran. It's not complaining about that. That is a lot of bytes. But we verified that there is padding there. Okay, so another thing that we could do here for checking is we could make sure that that position is not past the end. Panic, we could say root position is outside bounds of file. That's probably not something we need to guard against, but I'm just, I'm concerned about endianness. I'm worried that we get too big or too small a number by accident. But that seems to be the case. Okay, so we've got a trailer, so we've read the trailer part. And now what we could do is we could use that root position to get the first block. Now it doesn't say the block length of the root position, so we need to be able to kind of look at the 4 bytes and then and treat that as the length, and then get the rest of the slice and look at the level, and then Yeah, and then we have the data. Okay, so we have the trailer. We're gonna drive debug again. Let's make a block. And this is going to have a block len, just to keep the names consistent, is a U32. I think at that point we can read the level is going to be a U16. It's 2 bytes. And then we'll have data, which is going to be a slice of U8s, just like we've done previously. Okay. So probably what we want to give this is we want to give it something that starts at where that block len thing is going to be. The other option is, and I don't like this as much, is we give it a, borrowed slice, and then we, slice it ourselves. I think that we're going to have to slice it, but what we probably want is to do an unbounded, like starting with the start position of that block, and using the length that we read to slice out the rest of it. Yeah, okay, so block A. Now, before we do this, maybe what we could do is we could say root block. And this is going to give a block, right? Pub fun, because we're having fun. Okay, so here we could say let trailer is self.trailer, right? And then we want to do let's go ahead and do impl and we'll say new is data. We'll call it buffer. And this is going to be a slice of U8, and this is going to return self. And what we will do is we'll slice off the end of this. Start is trailer.root pause as usize, and we'll say block new, and we will do self.data start. Okay. So there we're slicing off everything except for where the root starts from. And it's interesting too that like this starts at the end, which makes me think that probably what happened in this file, because we're reading B10, remember, is that it writes the data pages first, and then so like the lowest level, and then the inner levels, and the root is at the end. Would make sense. We can probably verify that in the code later, but that's interesting. Okay, so now what we want to do is similar to this. What we will do is we will go block len, and we'll say 0 to 4. Okay. And we'll say level is U16 from BE bytes. This is going to be 4.6. And then we'll do data is going to be, and this is not self.data. We need to use buffer, right? We'll say buffer. That is going to be 6 to. Now here's where we need to check. We need to make sure. Okay, so let's say if block len is greater than 2. So let's do let data is that. If that's the case, then we do buffer 6 dot block len minus 2 as usize. I don't know if that's correct. Else it's buffer 6.6, right? So we'll just get an empty slice there. Okay, and what's wrong there? We need to borrow. Okay. Right, so I think we need the tick A here. And now it's like, this is unused, right? What's wrong there? Root block's never used. Okay, so yeah, because I think that we can get maybe in the next half hour, given how simple this file format is, we can read, so we got the root block on this tree. We can start to read entries from it. That might be cool. Let's see if we can use that. Okay. Let's debug. We don't need to debug the trailer anymore. Tree.root block. Okay, so we got some compiler warnings. Block length 855 level 1. That's interesting. So one level above. No, that's the base level. Remember we saw I don't know if I had that on stream or not, but that's B tree size level. Okay, never mind. So we don't. Interestingly, we see strings. So 109. We see strings of the same character, which is what we expected because that's what we put in the database, right? Let's look at the contents of this block. So and did we do big endian bytes? We did. Okay. Let's go and verify. I don't think that they would deliberately switch this, but let's go and verify that they're using big endian for the lengths of everything. Okay, that's probably not where it is. Let's look at the nursery. Maybe there's some information in here. Nursery, let me guess. Oh, this isn't even this is just a data structure. This is not a process. Okay. Okay. There's goop in here about expiration. I don't know if our file format has that in there. What I would like to find in the original code is where individual entries are written. Okay, so add key value. Let's go to, is that a cast? That's a cast. Okay, so it's key. So let's go to append node. That doesn't work because I don't have that set up. Okay, append node. Okay, so they've got some accounting going on here of the individual levels. Members, size, node size. Okay. Value count, tombstone count, bloom filter. Okay. So the top of stack node is at the level we wish to insert at. So let's just assume this is, we're at the level. Assert that the keys are increasing. So the inserting key, yeah, because this writer requires that keys come in order. Okay. Inserts it into the bloom filter. If it's level 0 and the value is tombstone. Okay, so this is incrementing the tombstone count or the value count. Note that tombstones only exist in level 0. Interesting. Okay. So then it's prepending the key and value onto the list. Okay, so then it might potentially go to flush node buffer. And right, so it reverses them. Okay, encode index node. This is what we want to look at. Blocks. Okay, so here's the note. This is the block, right? It's already encoded the block data. And then it's adding block size plus 2, so that includes the level, right? Let's look at encode index node. It's interesting this is in util and not like something like format. Encode index node. Okay. Okay, so v bisect, I don't know what that is. Hanoi 32. Okay, so that maps over this function. It puts tag end. So over here, remember tag end was FF. So we should see hold on. We're just looking at raw bytes here, by the way. We should see 255 in here somewhere in this section of things. But instead we're seeing 0. Okay. Okay, so let's look at CRC encapsulate KV entry. Okay, so we're not, let's forget tombstones, deleted. Okay, so It's just tag kv data. Okay, so kv data 2. Okay, so that's interesting. That says that's a time-stamped one, so it has an expiration on it. Interesting. I don't think that we have those. But we need to start looking at the entries in here, I think. Okay, so tag kv data, and then the key length, the key, and then the value. Okay, and this is like position length. These are the sorts of things where this is like pointer to another block, I guess. Okay, and then there's, so this calls CRC encapsulate. So these are this will prepend the CRC32, which is just using Erlang's built-in one, and then end it with the tag. Interesting. Okay, so I think what we need to do here is, I don't know if this is the correct slice yet. So I think what we should do is try to look into the data that we sliced out and make sure that it conforms to this format. So I think that compressed uncompressed 0 is correct, but what we should see is a 255 byte, and I'm not seeing that. It's 126, which is really bizarre to me. Why would that be? It's possible that so maybe we need to go up a level. So it should have tag end. Right. Okay. Okay, so that's encoded index node. Yeah. Right, and then it just, it writes it to the file, to the current index file. So it's just writing out a single block. Okay. Well, let's try to read that. So now, what we need to do is something like, maybe what we should do here is have compression. And this will be uncompressed and snappy and gzip. And I don't know if there were any other options there. Let's look back at the original. They don't tag that. So let's look for where they define the compression, which I think was down in here. We were looking at that. Yeah, so snappy, LZ4, gzip, none. Maybe we can use those words instead. Okay. None is a little bit overloaded. Let's say LZ4. And then we need to, there's probably a function in here that, yeah, so they've got these these definitions up here. Interesting, this file encoding says bisect in it, not Hanoi 2. Okay, so no compression. Let's just do one of these numbers. We can say this is repr u8, non equals 0, snappy is 1, gzip is 2, lz4 is 3. And then we can probably read that. I forget the details. There's stuff about like automatically implementing from for enums. I think that there's a guide about it. Let's see, enum enumerations. Casting. You can cast from the enum into a particular numeric type. Yeah. Okay. We might have to do that ourselves. Because you can't do like as compression, right? That's not going to work. So I think that what we want to add here is compression, and then looking back at this format, and then we have a skip byte. So maybe we don't want data here. We want KV, and then yeah, let's figure this out. So what we want is let's just see if we can do dot into. Let's say buffer. So this is going to be byte 7. And I think that, yeah, it's like, hey, it's not. We could pull in the derive more crate. I think it has a, you know, is there a try into implementation? No. Let's implement it. This is dumb. Okay, so we could do match self, and we say 0 is okay, compression none, And at one point in my work code, I did a ton of this, and it was really annoying. Um, and I was almost at the point of writing a proc macro that would do this for me. But then I think I found derive more, and I don't know that we need to do that for this. We'll say error, invalid compression value. Okay, so now we can convert that, and we'll say compression, right? And also here too, we'll need to say the block length is longer than 3, because we need to, let's call this KV. We need to do, this is from byte 7, right? And we can still just give the empty slice. KV. Let's see if we can still get that. Okay, expected identifier. What did I do wrong? Oh, I didn't finish that. Okay, invalid compression value. So there's something wrong there. Buffer 7 should be 0. Let's comment this out, right? And I think that we were, this was 6 before. I don't want to mess that up. And it started with a 0, did it not? Right. So what was, oh, the issue is this should be buffer 6, and this should slice from 7. Yeah. That's the issue. Okay. Okay, so if we go up and we find the compression, was none. Okay, so we got that part correct. And then our next step should be verifying that the following byte, and this is the other thing, is that we're going to have to keep incrementing this. That needs to be 8, because there should be a the tag end byte, right? We could do, is there cert a thing? Yeah, cert equal buffer 8. No. I'm sorry, I keep redoing that. But we know that there should be a tag byte. And that's going to panic, yeah. So it found 78. It should be 255. No. Buffer 7. Okay, hold on. I'm getting, okay, so there's 4 bytes. That's 6 bytes. That's 7 bytes. That's 8 bytes. So that should be 0 to 3, 4 and 5, 6, and 7. So that should be byte 7. Yes. And this should be 8 dot dot. I'm sorry. Block line -4. Yeah, so we could we should have FF right there. Let's double check real quick over here that when it's writing that block, that it's going to start with FF. Right, so tag end, which is in the header file as FF, right? I'm going to copy these over to the other. Let's just put them in a comment. Let's say const tag kv data u8 0x80, and let's just tag deleted 81 82 83 transact. I don't know what transact is. That'll be interesting to look into later. KV data 2 is 84. Deleted 2 is 85. And then tag end is FF. Okay, so we can go down here and say that should be tag end, right? I think this will still panic. Yeah, so it got 126, not 255. That's interesting. Why would that happen? Looking at this, we might need to hex dump this file. And I forget the flags for hex dump. Wish I had a GUI hex dump thing. Maybe for next time. Okay, so we're not getting... We're not getting that tag there. What else could it be? It could be the beginning of the length of a key value entry. We could look for these tags. Right. We could look for a 128. Let's remove this assert. And look for something toward the beginning of this buffer, which should be based on this this definition, should be a length. So after 8 bytes, we should have one of the tags, right? If we're doing this right. So 1, 2, 3, 4, 5, 6, 7, 8. Tag is 0, or there's zeros there. So that's 128, that's 129, 130. When we were seeing that assertion failure, yeah, I've lost the thread. Yeah, I think I cleared. Okay, we should see. There should be A255 between entries. We can clearly see the content changing. That's sort of interesting. You know, this 99. That's letter C. So we've got you know, that's C. 97 is going to be A, right? So we've clearly got data here. And note those are multiples of 2 in length because we picked the key and the value to be the same length. So that's like 4 A's as the key and 4 A's as the value. So what comes before that? There's an 8. So I would expect the key line 4 bytes. That's not right. Also, I'm getting a bunch of zeros at the end, not FF, right? $130 is one of those tags. Position length. I wonder what that 13 is. Okay. I think let me revert this. Let's not call it KV. Let's just call it data. And I want to include the compression byte in it. So let's do 6 again. And let's rename that to data. I know what it was like. The assertion was failing on, but what I don't know is like what we're actually seeing there at the head of this. Okay, so we read that it should be 0. 126 is not any one of those tags. It should be FF. (126) is 7F, so 1 minus tag KV data. No, it's 2 minus. 2 less than that. All right, this may be where we have to leave it because I'm kind of running out of steam. If you do think of anything, also Greg Bird, hit me up on Discord like you have been. Let's figure this out offline because I think that I should be seeing this byte here. We're clearly uncompressed. Now, there is a possibility that there's something more like this going on. I think this file encoding thing up here, yeah, it says bisect. So I think what's happening is the diagram's wrong. We need to look at this v bisect. Yeah, let's before we log off, I want to read this and we'll figure some things out. So binary code KV. Okay, interesting. We've got the key. So let's just look at this. The key and then the KV data tag and then the value. Rather than the tag and then the key length and then the key and then the value. So let's look at what this v bisect from ordict does. Okay, from ordict. Where are you? Okay, from GB trees from ordict. Okay, so let's look at from GB tree. This is better, slightly. Okay. Okay, the magic number is VBIS. Interesting. Okay, encode GB node. So we've got actually a different format here, I think. I'm not sure what the motivation of this is. And I think what I would like to do for the sake of our sanity, because there's some stuff going on here that is, yeah, really unclear to me. I'm guessing this has to do with encoding scans. I don't know. I guess so you could jump around files and do a binary search. yeah, I think what I want to do here is we're going to run our script again. Let's do Hanoi 2 here. And I think this is what's getting us into trouble. This format that's actually being used is not documented in that diagram. And you can tell because this makes no sense as compared to what the other one does. Whew. Yeah, okay. So this is about, it looks like, finding a key in the binary without decoding it into some other structure. That's what this is about. So each entry has like the current key. I want this bin size smaller. Okay, so this is the size of this. So this is like what keys are smaller. Yeah. Okay, this is a very very odd. And if we change this and let's we're gonna remove that, and we're gonna do rebar 3 shell. I need to make sure we were compiled. I think we were, but yeah, okay. Okay. Location ensure all started. HanoiDB. Oh, I'm in the wrong directory. Of course I am. Okay. Okay. So now let's do our load run dot. Okay. So now we've got, yeah, that's interesting. We got different stuff. No v bisect. Very interesting. Okay. So now over here, I'm going to remove, let's see, ls. Do I not have that? What was I? Do I not have that file? Interesting. Oh, because I removed it. Yeah, okay, so I need to remove it here. And we'll run that again. I should honestly do this as a like early val or something. Okay. So now, yeah, now we have, and let's run it one more time so we get, tombstones and different levels and stuff like that. Okay. And let's go back over to our Rust version, and we're going to CPR. Yep. Okay. Now let's run and see if we get something different. Okay, there's our 255 byte. So, okay, so the documentation was wrong because it was using a different file format. Oh, for Pete's sake. We wasted so much time on that. So let's real quickly put that assert back. And then we will, next time, we'll look at decoding entries. And we can, excuse me, we can match on, you know, what kind of entry it is. Okay, so thanks for coming, everybody. We'll see you next time.